Hello, and it's time to talk about line integrals. So we are here. This is not going to be all of 16.2. It's a really long section, so we're going to split into 2 days. So we'll do the second half on Monday. So you need to have watched this before class. So, what's a line integral? Well, picture something like this. Here's the way you want to think about this. We have our 3D grid. And let's say that we have a path we trace in the xy plane. We will call this path capital C. And we'll say it starts at point little a and ends at point little b. And it's a directed path. It's going in this. So, there is some function that determines height. So the idea is that as we go along here, we could look up and see, say, f of a. A is an xy point, and goes over to f of b. And what I want you to think of is kind of like a giant curtain that's up ahead. Big, twisty metal sheet where at every point the height is something different. Well, the integral then along this path would be the area of that metal sheet. And there are a few different ways you can think of this. It doesn't have to be physical area. It could be, say, you're passing through an electromagnetic field and collecting charge as you go. But the idea is the same as any integral, that as we go along this path or over this domain, we're adding up stuff. Well, we could straighten this out. What I said on the first day of class is don't reinvent the wheel. Let's put this in terms of what we already know. Z would be the height. Now, but along this axis, it won't be x or y, because x and y are both changing. We will call it s, where s represents distance along the path. It's not a coincidence we're using the same symbol as arc length. When we talked about arc length way back when, we used s to represent it. And so it's kind of the same thing. The length that we're traveling along this arc is going to be the independent variable. And so if we were to be able to straighten this out, that's not straight enough. We would have a point A, a point B. I guess normally S would start at 0, but well, and it would look like that. And then we could partition it the same way. We'd have a Riemann sum. However you want to do it, or you could use upper bounds or lower bounds or midpoints or whatever. That's once you take the limit, it all turns out the same. And so we would integrate that as z is f of xy. And so the area of each one of these would be f of xi star yi star. That is a point. If we were to take the path and split it up into little pieces like this, it would be a point from each interval times delta s, which is the width of each one of these rectangles. So you see here on any point here, let's put this in terms of xy. If I were to draw the path in xy, I would mark it as t equals a at the beginning and t equals b at the end. And so I would say, well, along the path, you'd have a bunch of little straight lines. Pretend these are all straight lines. And you would get this jagged zigzag pattern as you go. As usual, the more intervals we take, the more accurate it will get. And so we picked any 2 points here. Same thing. We'd have points xt, yt. We'd parameterize. We'll do examples of this. So it's possible that the theory is losing some of you, and that's okay, because we'll do some examples in a minute. But we would use this, and we would say, then delta S would have to be the distance along a straight line of, say, x of t, y of t, to x of t plus 1 and y of t plus 1, or ti and... No, that's a bad way of saying it. I'm sorry. That's a little confusing. Well, sorry. Let me try that again. That was a little confused there. We'll have a point here along the path that is x of ti and y of ti. We'd plug in the endpoints, and we would, the next point would be x of ti plus 1 and y of ti plus 1. And we could work out the distance along this using our standard distance formula, and it would allow us to get a straight line approximation. Using the Pythagorean theorem, the distance formula, it would be square root of this minus that squared plus square root of this minus that squared. Again, I don't want to get too caught up in the derivation, because those, I'm worried I've already made this way too confusing, and I want to show how we can do this when we know how to do the integrals. And like I've said before, in a practical real-world situation, you probably wouldn't be able to do the integral directly, but in our calculus world, we will be able to. So, this is the idea here. We're saying we have one of these rectangles. We're trying to sum up a bunch of rectangles. The width is delta S, and the height is f of xi star, yi star. And this is the ith rectangle. Again, if I talk about that, walking that curving path, it would be like if you, instead of walking directly on the path, you walked a bunch of straight lines, jagged between the different points. Well, you would, as usual with the Riemann sums, you would want to take the sum, where I goes from 1 to n. That would be sum up along all the different paths, and then you take the limit as n to infinity. So this is the way that we always do with Riemann sums. You want to write out a sum of a bunch of different rectangles, or anything you can sum, but usually I like to think of it as a rectangle. And then you want to take the limit as the number of them goes to infinity. That will equal the integral f of xy ds along a curve C. C was what we called as the curve from a point A to a point B. We want this to be a finite curve. We don't want to deal with curves that are infinitely long. You can, but we'd rather not. I guess this should say SI over here. though we usually assume they're all the same length. Okay, so how are we going to do this integral in practice? Well, in practice, we need to rewrite ds to be in terms of x and y, or even better, in terms of t. So let's go back to our arc length formula. If you don't remember it, we can review real quick. So if this is s, this is, or let's say dx right here. Dx means a small change in x, dy means a small change in y, and then ds would mean a small change in s. So the Pythagorean theorem comes into play here because it's a right angle. So we get ds would equal the square root of dx squared plus dy squared. Now that looks kind of ugly, but we are assuming these are all in fact functions of some parameter t. We have x of t, we have y of t, and then we would have s of t, which would be square root of x squared plus y squared. Remember back to when we talked about arc length, we said ds is good for some theoretical uses, the theorems work out better, but it's a pain to do for practical uses. We don't want to have to always change our parameterization to ds. I mean, we saw in the last section just how hard it is to change variables. So we're going to try to introduce this in terms of t, which t can be any variable. That should be ds here is equal to that. So I'm going to divide both sides by dt. And then I can bring the dt into the square root as a dt squared. So it'll be dx over dt squared plus dy over dt squared. Then I will multiply that dt over to the side. I think that t is part of that. Make it dt here. So this is part of the arc length formula. That's how we rewrite ds as dx over dt squared plus dy over dt squared. And if there's a third variable, if there's a z, you just do dz over dt squared as well. So that allows us to rewrite this in terms of any variable t. We can rewrite this integral as the integral from a to b of f of x of t comma y of t times square root of dx over dt squared plus dy over dt squared dt. So this little piece here is just our multiplier. It's kind of similar to the idea of the Jacobian. It's just something we have to do to rescale it so that the integral works in these new variables. I want to make one little note here that ds over dt, that is the change, how fast we are moving along this path, would equal to, if r of t, this was the old notation we used, r of t is the vector x of t and y of t, then ds dt is r prime of t square root of dx over dt squared plus dy over dt squared. The idea being that this square root part represents just sort of the distance, or it's a little hard to describe, the extra time it would take, for the fact of the curvature. But this absolute value of r prime of t is the speed, which just represents how fast we run along this curve. But it really shouldn't matter. If we're talking about measuring area, it shouldn't matter how fast we go along there. So we'll just say speed generally considered to be equal to 1. The idea is that it would cancel out with the dt anyway, or if we change the speed, we change the A and the B or something. The point is that however we worked it out, the speed that we run along the path will cancel itself out. So that's, if you, just by chance, if you look back there in notes, you saw ds dt equals this whole thing. The idea being that the speed we use doesn't matter, so we'll just set it to 1 to make it easier. All right, so enough theory. Let's get into some examples. How do we do this? Okay, so example here. Let's say we want to integrate along the path C function 2 plus x squared y ds, where C, we have to say what C is, what path we're integrating over. The upper half of x squared plus y squared equals 1. So the basic idea here is that we want to write x and y both as functions of a single variable we can then plug in. What is this? It's the unit circle. And it would need to say which direction it is. So we'll say counterclockwise. It will have to tell you, because if we go backwards, it will reverse the sign. So we are following this upper half circle counterclockwise. This means x, hopefully we know this by now, x will be cosine of theta. You can use t if you'd rather, but I'm going to use theta here. Y is sine of theta. Then we say we also need x prime would be negative sine of theta, and y prime would be cosine of theta. So our formula says we are going to evaluate this as, let's plug in here, 2 plus x squared, so that's cosine squared theta sine theta, times, let me erase this is kind of in the way, square root of x prime squared, so that's sine squared theta, plus cosine squared theta d theta. Well, that's just a 1. So we get, oh, and what are the limits? Well, theta starting at the right would be 0, and on the left would be pi. So we go from 0 to pi. So that will give us 0 to pi of 2 theta, or no, let me do this right. Let's back this up. Yeah, let's, all right. 0 to pi 2 theta plus integral from 0 to pi of cosine squared theta sine theta d theta. This is a u sub problem now, isn't it? We will say, okay, this first part will become 2 pi plus, and this integral, let's let u equal cosine theta, du is negative sine theta d theta. So we get negative integral of u squared du. Theta goes from 0 to pi, so then u would go from 1 to negative 1. And this should be pretty straightforward at this point. 2 pi plus integral from negative 1 to 1 of u squared du is 2 pi plus negative 1 to 1 of 1/3 u to the third is 2 pi plus 2 over 3. So that's our answer. All right. So let's just do some more examples. I'm just going to run through a few of them. And you come ask me during my office hours if there's anything about them you don't understand. Alright, so, example. Integral along c of x squared minus y plus 3z ds along the line segment from 0, 0, 0 to 1, 2, 1. Well, we need to parameterize this line segment, and so we've reached back to our ideas about parameterization with the different forms for writing lines, and I think the x of t would just be t, y of t is 2t, z of t is also t, where t goes from 0 to 1. So that's a path. We're going from time 0, 1, if we pretend that's this line segment. So we know what to plug in. And what about the ds? Well, ds would be square root of, let's see, x prime would be 1. Y prime would be 2. Z prime would be 1. So it would be 1 plus 4 plus 1, because we square each piece, is root 6 dt. So I like to think this is like a unit conversion. It's like, what this is saying is that S is distance traveled, T is time. ds over dt would then be something like root 6 meters per second. And so the idea is that we are starting off in, seconds, and we multiply by speed to get in terms of meters. As we said, our theory is that it always needs to be ds, needs to be in terms of arc length, of distance. So by multiplying this, we cancel out seconds and replace it with meters. We're in distance. We can do that without having to do the whole thing of rewriting s in terms of different variables. So that means we are going to have this. It will become integral. We said t goes from 0 to 1 of x squared, so that's t squared, minus y is 2t, plus 3z, which is 3t, dt. So I'm going to erase some of this other stuff now. Let's see. Integral from 0 to 1 of t squared plus t dt. Whoa, shoot. I forgot about the square root of 6. Can't forget that. Square root of 6 dt. ds is square root of 6 dt. So we need to replace it because the variables have to match. So t squared plus t, and then we'll put the root 6 out front. dt becomes root 6, 0, 1 of 1/3 t cubed plus 1/2 t squared, which would then become root 6, 1/3 plus 1/2 is 1/3 plus 1/2 is 5/6, so 5 root 6 over 6. That's my answer. Okay, so let's do some more. So I'm going to a path here. Let me make doing this right. All right. X and Y. We're going to take this path. Here's 0, 0. And here is 1, 1. And so we're going to say, let's take C1 to be a straight line path. Y equals X. And then go back C2 along the path Y equals X squared. So we've got two different paths here. And so if we define C as the whole path, so let's say we want to integrate X ds along C. Now this path would be called piecewise smooth. Piecewise smooth. And that basically means that if we can split it into pieces where each piece of it is smooth. There are no sharp corners or gaps or anything like that along C1. Same with C2. It's just when we switch between them, we can see it's a kind of a sharp turn. So we are going to separate this into integral along C1 plus the integral along C2. There's not really another way to do this because they're different paths, so we have to treat them as two separate integrals. Basically, piecewise smooth just means it's smooth except for a few points. So C1, let's write a path in terms of t. R of t, well this one's not too bad. It's x and y are the same, so we can just say it's t, t, where t goes from 0 to 1. But now C2 is a little trickier. So I would want to think of it as this. The x is decreasing from 1 to 0. So that means the x coordinate will be 1 minus t. And like I said earlier, we have to have a negative t there because it's going right to left. And so since it starts at 1 and ends at t, we can use various formulas like the line segment formula to work that out. Now that's for the x. And this is a thing we do with lines, with curves. If we can, if we've got in terms of y and x, we just basically describe x in terms of t, and then we use this equation here to tell us how to get y. Y is x squared, so therefore it is 1 minus t squared. And again, t will go from 0 to 1. Because it's going right to left, it covers the whole thing. So we now can do each of these separately using this parameterization. All right, so we're doing x ds. So integral for C1 of x ds, and I'll just do them both separately, would be the integral from 0 to 1 of x equals t. So I'll put in t. Then what's ds? Well, let's do a little sidebar here. Let's see. Derivative of x would be 1 because x and t are the same thing. So dx dt is 1. And then, 1 squared is also 1. dy dt would also be 1. So 1 plus 1 dt. So that's root 2 dt. So we'll multiply this t by a root 2 dt. So this then becomes 0, 1 of root 2 t squared over 2, which then becomes just root 2 over 2. So save that one. Okay, root 2 over 2 is the first piece. And now we need to do C2. All right, so let's do C2. So it'll be the integral of 1 minus t. Now there's no y in the integrand here, but there still is a y hidden in the ds, so we do need to use it. So let's do the derivatives. X prime of t, so the derivative of 1 minus t would be negative 1. Y prime of t, let's do derivative of this piece would be 2 times 1 minus t times derivative of the inside. Derivative of the inside is negative 1. Negative 1. So our ds here would be square root of 1 plus, and then square this whole thing, 4 1 minus t squared dt. So you get 1 minus t times square root of 1 plus 4 1 minus t squared dt from 0 to 1. All right, I'm going to erase some of this. And now we're down to a Calc 1 problem, which is what we always want to do, is reduce to Calc 1 problems. It would be a u sub, I suppose. U is always the entire thing under the square root, so u is 1 plus 4, 1 minus t squared. Then du, derivative of this, would be 8 times 1 minus t dt. So, okay, well, we've got a 1 minus t dt, so I'll just put an 8 here and a 1/8 here for balance, or use that other method that people like to teach. So it becomes 1/8 integral of, this is square root of u, so u to the 1/2, 8 times 1 minus t dt is du. And you could have tried to expand this out, but I don't think it would have helped because you'd still end up at the same derivative. What are the limits on u going to be? If t goes from 0 to 1, let's plug in 0 for t. I would get 1 plus 4 times 1 squared. If I plug in 0, I get 1 squared is 1, so it's 5. And if I plug in 1, I get 1 minus 1 is 0, so 0 plus 1 is 1. I might have missed... Oh, I did make a mistake earlier, and that is that when I did the du, I forgot the chain rule. We always forget the chain rule, right? Derivative of the inside here is negative 1, so this should be a negative 8 and a negative 1/8. So this is negative. Then you can flip the integrands to make it positive. It becomes 1/8 integral from 1 to 5 of 2/3 u to the 3/2. Which then 1/8 times 2/3 is 1 over 12. Then we'd have 5 to the 3/2 minus 1. So we just add these together. So the answer, the final answer, would be root 2 over 2 plus 1 over 12, 5 root 5 minus 1. And that's as simple as I think I would ask you to make it. You could combine these into a single fraction, but I don't think you need to. Well, let's keep going. I've got about 3 more examples that I'm going to go through. All right, so let's do the integral along C of x plus 2 ds, where r of t will be ti plus 4/3 t to the 3/2 j plus 1/2 t squared k. So this is some odd curve in 3 dimensions. And if you like, and we'll say t goes from 0 to 2. If you like, you could type this into GeoGebra and get an idea of what kind of shape it is. I'm really not sure what it would be. But we don't really need to, because we can do this entirely through algebra. We don't really need the visual on this one. Let's work out what r prime is. Is 1i plus 4/3 times 3/2 would be 2t to the 1/2 j plus t k. Another way, by the way, of shorthanding this, that whole square root of all the different stuff that we've been doing, would just be to say it is the length of r, the absolute value of r. Or I don't think you use double bars in this class. You just say it's the length of r prime. Sometimes use double piping for norms, for absolute value, magnitude. I'm used to that, but I don't think you do it in this class. All right, so we have that. So what this means is that would be, so I'm trying to say, ds could be written as absolute value of r prime times dt. It's just another way of saying the same expression. It's a little shorter than that whole long thing with a square root. So it would become square root of 1 plus 4t plus t squared. So be careful about this. We go to here, we take each component and we square it. 1 squared is 1. 2t to the 1/2 would be 4t when you square it. And t squared is t squared. So we plug in here, this is integral from 0 to 2 of, let's see, x is t. X is t, this is y, and this is z. So we only need x here, so it'll just be t plus 2 times square root of 1 plus 4t plus t squared dt. And so this is another u sub. We will say u will be the thing under the square root. U equals 1 plus 4t plus t squared. And again, I say this looks like a u sub. If you tried it and it didn't work, you try something else. And wait, hold on. Du, I'm talking while writing at the same time. Du would be 2t plus 4 dt. So that is the same as 2 times t plus 2 dt. So we can see it's almost the same thing. So I'll put a 2 here and a 1/2 here for balance. And again, if you'd rather solve for dt is du over 2t plus 2, that'll get you to the same place. It is 1/2 integral. Now, limits on u. T goes from 0 to 2. If I plug in 0 for u, I would get 1. Plug in 2 for u, I get 1 plus 8 plus 4 is 13. U to the 1/2 du. Because this 2t plus 2 dt all becomes a du. And now it's just the same old, same old. We get 1/2 times integral evaluate from 1 to 13 of 2/3 u to the 3/2 is 1/3 13 to the 3/2 minus 1 to the 3/2. Or if you prefer, 1/3 13 root 13 minus 1. Okay, now there is another thing I want to discuss, which is you can have the integrals not with respect to s, but with respect to x and y. So let's say it was given to you as c of fxy dx instead of ds. Well, this is actually a little bit easier because we can rewrite it as or from a to b, we will still need to change x and y to be in terms of t, because it's just easier if it's only one variable. But now we can rewrite this as dx over dt times dt. See, we divided by a dt and we multiplied by dt. It's balanced. So that means instead of doing the whole square root thing, we would just need to do dx dt, and that's all. And likewise, if it's y, I'm sure you can guess. Exact same thing, but with a dy over dt. The idea basically is that we're summing as the change in x and y. So it's like, even if we're going along some jagged path, we're just adding up the vertical change in x here, or in y at each step, rather than have to do both the x and the y together. So a shorthand way to write this, you'll see this a lot if you see c p of xy dx plus integral of q xy dy. Or even shorter, integral of p dx plus q dy. Mathematicians are notoriously lazy with our notation. We like to be as short and concise as possible. So this means p is a function of both x and y, so you'll have to plug in to replace them with t's. You'll replace the dx with dx over dt times dt. Same with the y's. So let's do an example of this. Okay. So I'm going to draw a picture of our path here. Or maybe two paths this time. That's an ugly y. So we will go from the point -5, -3, up to 0, 2. In a straight line. We will call that C1. And we will also go along a parabolic curve like this. That will be the equation x equals 4 minus y squared. And we'll call that C2. I want to integrate y squared dx plus x dy along C1 and also along C2. It is a good question you should be asking now is, will this give me the same thing? Does it matter which path I take? And that is actually a very important question for the remainder of this course. Does the path I do this integral along matter? Well, let's find out. All right, so let's do C1 first. So C1, it is parameterized as, I'm going to use the line segment formula. It's 0, 2 is the endpoint times t plus -5, -3 times 1 minus t. Which then we combine these, we get 0, 2t plus 5t minus 5 and 3t minus 3, which then we combine to get 5t minus 5, 5t minus 3, where t goes from 0 to 1. Now let's work out what the length of this thing. The length, the r prime of t, that we need to multiply by would be square root of Okay, the derivative of this first one is 5, so we have 5 squared. The second one is also 5, so we have 5 squared, so it's square root of 50, or 5 root 2. Is that right? I think I have this wrong in my notes, but that would be it, right? Yeah, my notes just say 5, but it would have to be 5 root 2, because I take the derivative of each piece, and then I square it and add them together. Yeah, so I would get 5 root 2. So, okay. So, that's the length. So, I need to do that integral now. So, 5 root 2 is my multiplier. That's the point I was trying to make. Let me zoom out a bit here so I can see it. All right, so, on C1, so it would be the integral from 0 to 1 of, okay, y squared. Y is 5t minus 3. We'll have 5t minus 3 squared times dx over dt. Oh, we don't actually need this, do we? Because, like I just said, since it's dx, we just dx over dt is 5. So we just multiply by 5 dt instead of that 5 root 2. So, yeah. And then for the x part, yeah, so basically I'm saying my notes were confusing, and I hope it didn't confuse you too bad. You're with me now. Integral from 0 to 1 of x is 5t minus 5. dx dt and dy dt are both 5. So I will get x is 5t minus 5 times 5 dt. And then, honestly, this is just turning the crank, so I'm just going to skip to the end here. It ends up as negative 5 over 6. And I encourage you to work it out, but, well, you should be able to do this in your sleep at this point, since it's all just polynomials. I would expand the left side, or you could do a u sub, yeah, whichever you prefer. Okay, so negative 5 over 6 is what we get. But now let's try the other path. So let me erase this here. And let's see what happens if we go along the other path. Okay, it says 4 minus y squared. Now we're still going from the negative 5, negative 3 up to the 0, 2. Now the way it's listed this time, y is the independent variable. So I think the easiest thing for us to do here would just be to say that y goes from negative 3 to 2. So therefore we can just say y equals t. Because if you wanted to, you could try to solve this for y. Y equals square root of something, but it would actually not be 1-to-1. There'd be a plus or minus involved because it does involve vertical line test. So it would be easier just to leave it this way. Let's set y as t. Then x would be 4 minus t squared. So y prime is 1 and x prime is negative 2t. So then when we want to do this integral, it would be integral, okay, y squared is just t squared times dx, x prime is negative 2t, so negative 2t dt. And y and t goes from negative 2 to 3. In fact, we can write this here as t as well. Plus the integral for x is 4 minus t squared. And then dy, well, y prime is 1, so dy and dt are the same thing. Negative 2 to 3. Or negative 3 to 2. What am I? This is the one disadvantage of teaching online, is that no one's here to yell at me when I make these obvious mistakes. Okay, so that's an integral. Once again, I think you can handle it from here on out. But the answer we get is 40.83 repeating, which is very different than what we got the other way. Hence, we can say line integrals are path dependent. Like I said, this is an important observation. We learned back in Calc 1 the fundamental theorem of calculus, which said if we were doing an integral, we can just plug in the end point and the starting point and subtract and get an answer. Here it's saying we can't do that. We know the end point, we know the starting point, but that's not enough. We also have to specify how we get from one to the other. Sometimes. And other times, it turns out it doesn't matter at all. And that gets into the idea of conservation of energy. And so the idea that we will learn in the future, Tuesday I think, is that sometimes there are conservative fields where it doesn't matter what path you take, and sometimes there are ones where it does matter. What we're saying from here is, here's an example where the path you take matters. Two different paths give two different results. Now, if we knew that they were independent, we could just use the easiest path, but we don't. So we have to be careful. Okay, let's do one more example. Then I will call it a day or a night. For me, I don't know what time it is for you. But we'll go along a spiral C in 3 dimensions. It'll be cosine of t, sine of t, and just plain t, where t goes from 0 to 2 pi. So we've seen this before. It's like a spring or a spiral going up into the air, and we're doing one circle of it. This is r of t. What would r prime of t be? Well, let's do the derivatives. We will get negative sine t, cosine t, and 1. So then the length of r prime would be square root of sine squared t plus cosine squared t plus 1 squared, which is square root of 2. So we want to say, let us integrate the function y sine z ds. I got a little ahead of myself. I probably should have written out the problem before I started solving it. But yeah, so we need to write this. So this will become the integral from 0 to 2 pi of, okay, y is sine of t. Z is t, so it's another sine of t. Then ds would be root 2 dt. So 0 to 2 pi of root 2 sine squared t dt, which then becomes, let's pull some stuff out here, root 2 integral from 0 to 2 pi of 1/2 1 minus cosine of 2t dt equals, Okay, root 2 over 2. Pull that 1/2 out. 0 to 2 pi of t minus 1/2 sine of 2t, which equals root 2 over 2, 2 pi minus 1/2 sine of 4 pi minus 0 minus 1/2 sine of 0. 0, 0, also 0. 2 and 2 divide out, we're left with root 2 pi. Okay, so that's the basics of it. This is how to do most of these problems, and like I said, come ask me if you have any other questions. I will be around my usual time from 4 to 5 on Monday in the calculus table, and we will have a quiz, so be ready. Bye.